To Educator.com, and welcome back to AP Chemistry. So today we're going to continue our discussion of buffer solutions, and after this we're going to go even further with buffer solutions. So last time we introduced what a buffer solution was. We said that it is a solution made up of a weak acid plus the salt of its conjugate base, or it's a weak base plus the salt of its conjugate acid. And it is designed for one thing only. It is designed to resist changes in pH once you add acid or base to that buffer solution. So we make a buffer solution at a specified pH that we want, and we design it specifically so that if you add acid or base to it, the pH doesn't change. Or if it changes so slightly that it's negligible. That's what a buffer is. So today we're going to talk about how buffer solutions actually work. In the last lesson, you remember we actually created a buffer solution, two of them in fact. We did one with hydrofluoric acid and sodium fluoride. And then the last one that we did was we did acetic acid and sodium acetate. So we ended up with a pH of about 4.66. So here we're going to talk about how buffers actually do what they do. In other words, resist changes in pH. So let's get started. Now, let me just write down something real quickly. So what it is that we actually said about buffers. So we said that a buffer solution is a solution at a prescribed pH that resists changes to that pH upon addition of H plus or OH minus. Again, when we add acid, we're adding H plus. When we add base, we're adding OH minus. That's what we mean by adding acid or base. Ultimately, this is the acid, this is the base. That's what's important. The cations, the other anions, excuse me, the other ions don't matter. Okay, how does this happen? That is the question. How? How does this happen? Okay, so let's take a picture of a buffer solution. We have a choice. We can either do acid, salt of conjugate base, or base or weak base, salt of conjugate acid. Let's stick with what we've done, which is a weak acid plus the salt of its conjugate base. So hydrofluoric acid. So we have some HF floating around in solution, some HF floating around in solution, some HF floating around in solution. We have the salt of its conjugate base. So let's ignore the cation. Let's just deal with the fluoride ion. We have some F minus floating around, we have F minus floating around, and we have F minus floating around. Now it's true, we also have a little bit of H plus floating around. I'm going to put a circle around it, H plus floating around, some H plus floating around. Now here's the idea. How does something resist a change in pH? Well, how does pH change? Well, hydrogen ion concentration changes. It changes one of two ways. It changes by either going up or going down. If I add acid to a solution, I've added more hydrogen ion to the solution, so the hydrogen ion concentration goes up, the pH drops. If I add base to the solution, any normal solution, I'm not talking about a buffer right now, any normal solution, well, the base ends up its hydrogen ion, the hydroxide ion concentration rises, the POH drops, the pH actually rises. That's what's going on. So what we want to do is resisting changes upon addition of acid or base means if I add acid, how can I eat up that acid so it doesn't float around freely in solution and change the molarity of the hydrogen ion concentration? In other words, how can I sequester it? How can I bind it? How can I lock it up so it isn't just floating around freely, changing the concentration of the hydrogen ion? And if I add base, how do I bind it? How do I lock it up? How do I pull it, get rid of it, so it doesn't actually end up reacting with the hydrogen ion concentration and dropping the hydrogen ion concentration and raising the pH? That's the whole idea of a buffer. How does it do that? Here's how it does that. If I add base, which is OH minus, right? I add base. Here's the reaction that takes place. So let's say all of a sudden I drop in some base, which is OH minus. Well, the OH minus is a strong base. It does one thing. It's going to seek out hydrogen ions. So the base that you add is going to seek out hydrogen ions. Well, the only source of hydrogen ion, actually, let me erase these because these actually will just get in the way and confuse you. What's important in a buffer solution is the acid and its anion. The only source of hydrogen ion in a buffer solution is right there, is the H's, are these H's right here. So when I drop in OH here, the OH is going to pull off these H's, and here's the reaction that's going to take place. Plus HF, it's going to form HOH, which is water, acid-base neutralization, plus F minus. So what it's going to do is it's going to, so what did we say? We said if we add base, we need to wait to bind that base so it doesn't affect the hydrogen ion concentration. Well, here is your binding right here. If you add base to a buffer solution, it reacts with the hydrogen fluoride. The hydrogen fluoride is there for that reason. It's there to react with added base, production of F minus ion, and water. Water is neutral. F minus doesn't really affect anything all that much in this solution. So what we've done is we have sequestered the hydroxide by making it react with a hydrogen on the hydrofluoric acid to produce water and F minus ion. So now it isn't floating around freely, affecting the hydrogen ion concentration. Now, if we add acid, which means adding H+, well, H+, here's what's going to happen. It's going to react with the F minus now. So if I add acid, now the F minus is there to react with it, to sequester it, to bind it so that it's not floating around freely. Because F minus is a strong conjugate base, HF is a weak acid. It's going to be mostly in that direction, not mostly in that direction. That's what the equilibrium says. So F minus reacts with any excess acid that we add on top of what the pH is to produce HF. It binds the hydrogen ion so that the hydrogen ion is not floating around freely, contributing to the concentration of free hydrogen ion. The measure of the acidity of a solution is based on the concentration of hydrogen ion. A buffer solution has free base floating around, the F minus, that's the conjugate base of the weak acid, to react with any extra acid that I might add to bind it so that it isn't floating around freely. It also contains the weak acid itself to react with any base that I might add so that the base doesn't float around freely. That's the whole idea. That's all a buffer solution does, is it binds any base or acid that I throw in there and keeps it from doing any damage. It keeps it from changing anything. It's as if, so that, remember those H pluses that I initially erased? It's so that these H plus concentration stays reasonably the same. If I add H plus, it would go up if these F minuses weren't there. Because the F minuses are there, they bind the added H plus, so they're not floating around freely. This is constant. OH minus, if I add that, these are there to react with the OH minus to bind it so that it doesn't pull these out of solution and reduce the hydrogen ion concentration. That's what a buffer solution does. And this is how it does it. Okay.